Have you ever looked up into the vast, dark canvas of the night sky, dotted with its countless points of light, and felt a profound sense of wonder? Have you ever asked yourself the biggest question of all, are we alone? For millennia, this question was the domain of philosophers and poets. But today, it is a scientific investigation, an active, thrilling pursuit of knowledge that takes us to the frontiers of the cosmos. We search for the answer by looking for worlds beyond our own, for planets orbiting other suns. We call them exoplanets, and they have completely revolutionized our understanding of the universe and our place within it. They are the new frontier. So, what exactly is an exoplanet? The definition is refreshingly simple. It is a planet that exists outside of our solar system. Think about it. Our little neighborhood, with its 8 planets circling our sun, is just one of countless planetary systems in the Milky Way galaxy alone. An exoplanet is a world that orbits a different star, a distant sun that might appear to us as just another faint star in the night sky. These extrasolar planets, as they are also known, are not just science fiction concepts anymore. They are real, tangible places that we can detect, study, and dream of exploring. Each one is a new piece in the grand cosmic puzzle. These distant worlds are fashioned from the very same cosmic ingredients as the planets we know and love right here at home: hydrogen, helium, carbon, oxygen, silicon, iron. This means exoplanets can be just as diverse as the worlds in our own solar system. Some may be rocky and terrestrial, like Earth or Mars. Others could be colossal spheres of swirling gas, like Jupiter or Saturn. And some might be entirely new categories of planets, defying our expectations and expanding our cosmic imagination. The universe, it turns in, is more creative than we ever thought. The sheer variety is staggering. We are finding worlds that challenge our neat and tidy models of how planetary systems should form and behave. Imagine a planet where it rains glass sideways, or a world perpetually shrouded in darkness on one side and scorched by its star on the other. Let's take a tour of this cosmic zoo. One of the most common types of planets we have found are the gas giants, much like our own Jupiter, Neptune. These are massive worlds, composed primarily of hydrogen-helium, with no solid surface to stand on. They are behemoths, gravitational kings of their systems. Some of these gas giants orbit their stars at distances similar to our own outer planets. However, we have also discovered a particularly surprising subcategory: the hot Jupiters. These are gas giants that orbit their parent stars at an incredibly close range, sometimes completing a full orbit in just a few Earth days. Their proximity bakes them to extreme temperatures, making them fiery, turbulent worlds, unlike anything in our solar system. Then we have the super-Earths. This is a fascinating category of planet that we don't have in our own solar system. As their name suggests, super-Earths are planets more massive than Earth, but less massive than our smallest gas giants, Neptune, Uranus. They occupy a size and mass range that is tantalizingly in between. These worlds could be rocky, like a scaled-up version of our own planet, or they could have dense, crushing atmospheres. Some might be water worlds, completely covered by a global ocean hundreds of kilometers deep. We don't yet know if a super-Earth could be habitable, but their prevalence in the galaxy makes them a prime target for future study. Of course, the category that captures our hearts and imaginations the most is the Earth analog. These are the holy grail of exoplanet hunting. An Earth analog would be a planet similar to our own in several key ways: size, mass, composition. Crucially, it would also orbit its star within the habitable zone, sometimes called the Goldilocks zone. This is the region around a star where conditions are not too hot and not too cold, allowing for liquid water to potentially exist on the planet's surface. And as far as we know, liquid water is a fundamental prerequisite for life as we know it. Finding a true Earth twin remains a primary goal for astronomers. These categories are just broad labels we use to make sense of the data. The reality is likely a rich and complex spectrum of planetary types. We see lava worlds, ice giants, planets with rings that dwarf Saturn's, and even rogue planets that wander through interstellar space untethered to any star. Each new discovery adds another brushstroke to our portrait of the galaxy. The universe is a vast and creative laboratory, and by studying these different types of exoplanets, we learn not only about them, but also about the physical and chemical processes that govern the formation and evolution of all planets, including our own precious Earth. Finding an exoplanet is an incredible technical challenge. You have to remember how far away and how small these objects are. Imagine trying to spot a firefly on the edge of a searchlight from 100 miles away. That's the scale of the problem. A planet gives off no light of its own. It only reflects the faint light of its parent star. That star is 1 billion times brighter, overwhelming the planet's tiny signal. So direct imaging is extremely difficult. Possible only for very large planets that are very far from their stars, and even then it needs sophisticated techniques. To get around this glare, astronomers use clever indirect methods. The most successful is the transit method. Beautifully simple in principle. We stare at a star and watch its brightness very carefully over time. If a planet's orbit is aligned from our view, it will periodically pass in front of the star. When it does, it blocks a tiny fraction of starlight, causing a slight temporary dip in measured brightness. This dip, or transit, signals a planet. Kepler Space Telescope, TESS. They've discovered thousands of exoplanets. It's like a cosmic census, staring at hundreds of thousands of stars at once, waiting for telltale winks. The size of the dip tells us how big the planet is relative to its star. How often dips occur tells us the planet's year, its orbital period. Repeated transits let us build a picture of the planet's size and its orbit, crucial first steps in characterizing a new world. Transit opened the floodgates of discovery, but transits are just one tool. Another powerful technique is the radial velocity method, sometimes called the wobble method. The planet and star orbit their common center of mass. The star, being far more massive, barely moves but executes a tiny wobble. As the star wobbles toward and away from us, its light is subtly altered by the Doppler effect, the same effect that changes the pitch of a passing siren. By measuring those tiny shifts in the star's light, we can deduce an unseen planetary companion and even estimate its mass. Section 4, the wobble, the wink, and the warp. A deeper look at detection. Let's dig a little deeper into these ingenious detection methods. The radial velocity, or wobble, method found the very first exoplanet orbiting a sun-like star. It relies on spectroscopy, breaking starlight into its colors, like a rainbow. Within this spectrum are dark absorption lines tied to elements in the star's atmosphere. As the star wobbles under a planet's gravity, these lines shift slightly toward the blue as the star moves toward us, and toward the red as it moves away. It's a delicate dance, but instruments can measure it. Direct imaging is challenging, but increasingly feasible. The key is canceling the star's overwhelming glare. Astronomers use coronagraphs, masks inside telescopes that block starlight. Adaptive optics correct atmospheric blurring for much sharper images. So far, this method has revealed young, massive, hot planets glowing in infrared light, often far from their stars. It's the closest thing to a baby picture of another world. Next, gravitational microlensing, straight out of Einstein's playbook. Mass warps the fabric of space-time. A foreground star can act as a lens, bending and magnifying light from a background star. If the foreground star has a planet, that planet adds a brief spike in magnification. 1 in a million alignments, rare and non-repeatable, but uniquely powerful, detecting planets of all sizes and even rogue planets not bound to any star. Finally, astrometry, the oldest branch with a high-tech upgrade. It measures a star's position in the sky precisely over many years. A planet's tug makes the star trace a tiny circle or ellipse against distant stars. incredibly small, like measuring a human hair's width from miles away. Missions like ESA's Gaia are now making astrometry a powerful planet-finding and weighing tool, completing our toolkit for finding new worlds. Section 5. From Speculation to Science, a brief history of discovery. For most of human history, worlds beyond our own were purely a matter of speculation. Ancient Greek philosophers debated the existence of other worlds, but without any evidence, it remained a philosophical exercise. For centuries, the idea lay dormant, occasionally resurfacing in the writings of visionaries. But the scientific search for exoplanets is a very recent story. It wasn't until the latter half of the 20th century technology and theory began to converge, allowing us to seriously entertain the possibility of detecting these faint and distant objects. The journey from imagination to observation has been a rapid and exhilarating one. The first confirmed detection of an exoplanet was actually a bit of a surprise, and it wasn't around a normal, sun-like star. In 1992, astronomers Alexander Wolszczan and Dale Frail announced the discovery of two planets orbiting a pulsar, a rapidly spinning, dead stellar core. These pulsar planets were bizarre, likely formed from the debris of a supernova explosion. While a landmark discovery, the real prize was finding a planet orbiting a star like our Sun, a place where life as we know it might conceivably arise. That breakthrough was just around the corner, marking the true beginning of the exoplanet era. That watershed moment arrived in 1995. Swiss astronomers Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, the first exoplanet confirmed to be orbiting a main sequence star similar to our Sun. They used the radial velocity method, detecting the star's telltale wobble. The planet they found was a shocker, a hot Jupiter, a gas giant larger than Jupiter, orbiting its star in a blistering 4-day period. This discovery shattered existing theories of planet formation, which held that giant planets could only form far from their stars. It proved that the universe was more complex and surprising than we had imagined. Since that first discovery in 1995, the field has exploded. The initial trickle of discoveries became a flood, thanks largely to the incredible success of NASA's Kepler Space Telescope. As of today, in early May 2026, the number of confirmed exoplanets has surpassed 5,000, with thousands more candidates awaiting verification. We have gone from knowing of only one planetary system, our own, to knowing of thousands. Based on these findings, statistical estimates suggest that planets are not the exception, but the rule. It is now thought that on average there is at least one planet for every star in the sky. Do the math. In our Milky Way alone, that's hundreds of billions, perhaps a trillion, potential worlds. Section 6. The Ultimate Search. Why exoplanets matter for humanity. So why do we do this? Why do we spend billions of dollars and countless hours of human ingenuity? To find these distant specks of rock and gas? It's more than just an academic exercise. The search for exoplanets is fundamentally tied to the search for life beyond Earth. Scientists, astrobiologists, use the data we gather to assess potential habitability. They examine a planet's size, its mass, and its location relative to its star, to see if it lies within that promising habitable zone where liquid water could exist. The next great leap in this search is to study the atmospheres of these exoplanets. When a planet transits its star, a tiny amount of starlight passes through its upper atmosphere before reaching our telescopes. By analyzing the spectrum of that light, we can look for the chemical fingerprints of different gases. Are there signs of water vapor, carbon dioxide, methane? What we are really looking for are biosignatures, gases like oxygen. Finding a combination of gases like oxygen and methane in an exoplanet's atmosphere would be a stunningly powerful indicator of life. This grand endeavor also provides a profound context for our own existence. By studying thousands of other planetary systems, we learn what is common and what is rare. We see systems that are wildly different from our own, which helps us understand the chain of events that led to the formation of our solar system. Is a stable system with a large moon and a protective Jupiter a common setup, or are we the result of a lucky cosmic fluke? Exoplanet science helps us move from a sample size of 1 to a galactic perspective. As we stand here in 2026, we are living in a golden age of discovery. With new, more powerful instruments like the James Webb Space Telescope already delivering breathtaking data, and with even more ambitious missions on the drawing board, we may find strange and beautiful new worlds. We may find the chemical precursors to life. We may even find definitive proof that we are not alone. So, the next time you look up at the night sky, remember that it is not empty. It is filled with worlds, with possibilities, with the promise of discovery. The search continues, and who knows what wonders we will find next.